Hello children, ready, set, do this problem. The answer is 300 newtons. It's worded like a third law question. The third law tension force on the worker from the crate is 600 newtons, but if the weight of the crate is 300 newtons downward, it must be held upward by the floor with the same force, not due to the third law, due to how floors basically work. Okay, so we're gonna do a little more forces. We're almost at the end, but let's watch a fascinating. No, we're gonna tell a fascinating story. So way back in the old days, when I was in high school, we used to not have phones. We used to take paper and write notes to each other. We would say, like, "Oh, I love physics," and then we would pass these notes to each other on paper, and then read them and say, "Oh wow, very cool! Wow, what a great story." But we were always really careful because if our teacher ever saw us passing notes, the teacher would take the note and read it to the whole class, and we would be super embarrassed. That would be the worst thing ever. So if a teacher comes around and tries to pull the note away from me sideways, I would definitely have to grab my hand and go, "No, not my note, not my secret private life," and push down really hard to stop my teacher from taking my paper and reading my note. So let's draw a quick diagram of that. Wrong marker. Hopefully this is not permanent. Yeah, no one will tell that. There's me, sitting in class. There's my note. There's my physics teacher. My physics teacher is going to grab the note and pull sideways. I'm going to take my hand and go, "No, not my secret private life," and push down. So here's a free body diagram for the paper, the note. There's some tension. It's being pulled sideways. There's a tiny little bit of weight. Yeah, Fg. Paper, as you guys know, has very small mass. There's a tiny little bit of normal force to counteract that weight. They're so small, I'm going to mostly ignore. No, I'm not going to ignore that. They're very small, pretty insignificant, as you would say. Wait a second. I pushed down really hard on the paper. With a normal force. What force is preventing the note from being moved to the right? What's that? Yeah, that's right. It is friction. Friction. Now let's look at some kind of weird inconsistency. If I want to prevent the paper from being pulled away, I push down harder. So if Fn increased, this is not really how, that's not very clear. If Fn increases, that makes Ff increase. But that doesn't make any sense. Oh, I'll call this F flam, because it's from me, Mr. Lamb's force. This is teacher force. Okay, it's fixed, it's fine. So, how come I pushed down to increase the sideways frictional force? Well, yeah, the paper is so thin, I can't grab the paper and pull it with tension, then it'll just like rip in half. But this should contradict something we said. We said before, vertical and horizontal are independent. They don't affect each other. But in this case, it does. Why is that? How come the greater I push down, the more friction there is sideways? Good question. Well, here's a big hint. The greater I push down, the more the normal force. The more the normal force from the table on the paper. I call this normal force. It is a normal force from my hand on the paper. So the harder I push down with my hand on the paper, the harder the table has to push up on the paper. That makes sense. That's true. That's correct. Gravity is very, very small and negligible, but there is a pretty big normal force on the table. Not because of gravity, but because I'm pushing down so hard. So this is a really important idea. If I ask the class what factors affect the force of friction, a lot of people say gravity, the weight of the object, the mass of the object. It's actually not the mass or weight of the object. It's the normal force between the object and the ground or the surface where there's friction. Why is that? Imagine you had a microscope and you looked really closely at your desk, and hopefully you didn't find anything gross. The desk, it feels smooth to you, but if you look super microscopically, it actually has lots of little rugged imperfections and roughness and holes and crevices and just weird stuff. It's not perfectly smooth, it's rough. And paper also feels smooth, but if you zoom in super, super close, paper, or any object, really, it's not smooth on the bottom, it's always rough. Some objects are more smooth, like Teflon. Some objects are less smooth, like, I don't know, rocks, the sweaters. But no matter what, they're never perfectly smooth. And this is why there's friction, because these little cracks and rough edges interact and interlock with each other. And they interact and interlock with each other more if there's more and more normal force. So great, we did it. We're super scholars. We figured out the formula for friction. F equals mu Fn. It's obviously on the equation sheet, but if you wanted a nice way to remember it, friction equals mu normal. Friction it's fun. Physics is fun. Oh yeah, right? Yes, exactly. This is a mu. It's not an M, it's not a U, it's some kind of Greek combination of the two. We just ran out of letters, so we're using mu right now. And this stands for the coefficient of friction. Remember how I said that some objects have a lot of friction, some have very little friction, some have a lot of these rough edges, some of them don't? Yeah, something like wood is probably, if you just chop it straight in half, you have some rough wood, that's very rough, there's a lot of friction. If you have some nice smooth plastic, made in a very nice factory, and I don't know, then it might have very little roughness, it might have much less friction. So wood would have a high mu, plastic would have a low mu. In fact, actually, that's not really true. For a mu, you need two materials, not just one, because they have to interact with each other. So wood on wood would probably have a very high mu, plastic on plastic would have a low mu, but some combination like plastic on wood would have something in between. That was a lot of information. You don't have to memorize or know any of them. They're all right here. There's a list on the equation sheet. No, there's a list on the Regents reference table. There's a list in the book. There's a list right here. You can also Google them very easily, but it makes sense. Ice on ice? Oh, ice is very slippery. Of course, we have very low values of mu. Rubber on dry concrete? Ooh, that sounds like they're both very rough. A very, very high mu. Mu is always, almost always, less than 1. Sometimes it can be higher for very, very rough things, but it's usually some decimal less than 1. It always depends on two surfaces, and it has no units, because if you look, it's actually a ratio of force to force. If you solve for mu, you get force over force, newtons over newtons. So it does make sense that there are no units at all. For mu, the coefficient of friction. Coefficient of friction. Great. Okay, we're going to watch a fascinating video because there's one more thing to talk about when we talk about this. I'm not certain. There's like 10 more things. Okay, watch this video. So in this video, It's like a Japanese game show. They're trying to climb these stairs. The stairs are covered in oil, so it's super slippery. The oil's coming out of those like giant faucets. It looks kind of gross. They really want that treasure chest. Oh no. Alright, let's watch a little more. Maybe over here. Okay. Oh, they're almost there. They're almost at the top. No. Too bad. Okay, so something to notice about this video. Once the people in the video started slipping down the stairs, did they ever stop? No, pretty much once they start sliding, they slide all the way down to the bottom and just start all the way over. It's a pretty tough game, I'm sure. There's one more thing. If a box and a table, if the box is just sitting on the table at rest, not moving, not sliding, there'll be a lot of friction. But if I push it and push it and push it and push it, and it starts sliding, or I just throw the box on the table, or the box is just dropped on the table and right when it lands, what's going to happen to all these little cracks and crevices? Are they going to be as interlocked as if the box is stationary? It will not, no. There's two mu's. One for when something is sliding or moving, kinetic. And there's one for something that's stationary, not sliding, static. So when the objects are stationary or not sliding against each other, use the static mu. When they are sliding, use kinetic. And hopefully you can guess, well, if they're static, there's more friction. So mu s is almost always greater. I can't think of an example where it would be. Mu s is greater than mu k. Mu s, mu k. This opens up a really interesting idea. I know most of you guys don't drive, but imagine this. You're driving your car down the road. It's super icy or super wet, whatever. The road's slippery. So you press your brakes, but your car doesn't fully stop. The wheels stop, but since it's so slippery, the wheels, which are not turning, are sliding across the road. What should you do? Should you press the brakes more, or maybe let go of the brakes? What do you guys think? If you press the brakes, the wheels stop, but they keep sliding. Should you press the brakes more or let them go? Tell me right now. You guys ready to have your minds blown? If you press the brakes and the car doesn't stop, you should actually let go of the brakes and then press them again, and then let go, and then press them again, then let go, and press them again. Because kinetic, well, the question is, in which category does rolling fit in? People think, oh, rolling, well, if the wheels are rolling, the car is moving, so it's kinetic. It's not. Rolling is static friction, because the wheels aren't sliding. Normally when you drive, the wheels don't slide across the road. Normally when you drive, the bottom of the wheel grips the road, and then the wheel turns, and then another part grips the road. But every little piece of tire, when it touches the ground, doesn't slide. The whole tire rolls. So there's actually a little trick. You have to release the brakes, and then your car tires will start rolling, and then you'll go from kinetic to static friction, and then you press the brakes again, and then your car will stop better than if you just held the brakes. Actually, forget all that, because modern cars don't have that problem. Modern cars will do that automatically. The car will detect if your tires are sliding, and then it will release and press and release and press and release and press, release and press really, really fast. Much faster than you could, and it'll hopefully save your life. Here's a video explaining that.
When the driver fully applies the brakes in a vehicle without the anti-lock brake system, the brakes can lock. This causes the wheels to stop turning, which makes the tires skid. Skidding tires have very little grip and are not effective at stopping or turning the vehicle, so the driver may be unable to take evasive action. With ABS, when the driver fully applies the brakes, the system uses sensors to detect any brake lockup and rapidly pulses that brake to prevent it from locking. This helps to prevent skidding so the tires can maintain grip. It also helps to allow the vehicle to be steered around obstacles while braking. One way to think of ABS is allows braking and steering.
Okay, so that's anti-lock braking system. You don't really need to understand it in order to drive, but you do need to understand it for physics. By switching from kinetic to static, the car gets more friction. And a really important idea for later, rolling is static, not kinetic. When an object rolls, the bottom is not sliding in under ideal rolling. And that's what kind of talk about in the future. So we'll do some practice problems. Let's say I have a hypothetical 10 kilogram rubber crate or cube or whatever on a nice concrete level surface. Let's keep it real simple. Mu s is 0.9. Mu k is 0.8. So I just take this rubber cube, and just plop it on the concrete. It's horizontal flat concrete. And around G, let's say G is about 10 meters per second squared. Find FF for me. Find FF. If I take the cube and just leave it in the middle of a flat concrete floor, find FF. What's that? You said it's 90 newtons? No, it's 0. Draw a free body diagram. Fg will be 100 newtons. Thus, Fn, 100 newtons. Unless the cube will start flying or sinking into the ground, they must add up to 0. Alright, if you said that FF is 90 newtons, which way? Left, right, up, down? No. If you don't, this is a weird thing. If you don't need friction, this is going to sound weird. If you don't need friction, there won't be friction. Just think abstractly. Don't think about physics. What does friction do? It slows things down or stops them from moving. This cube, I said I put it flat on the floor. It wouldn't start moving for no reason. Things don't move or accelerate unless there's a net force on them. There's no force sideways or anything. So it will have no friction at all. This is a lie, but we can fix it with one line. Bam, amazing. We made an inequality. This is the maximum value of friction, but it could just be 0 if there's no movement or other forces to oppose. So let's say I'm pulling this cube with some force Ft, tension. If Ft were 90 newtons, then yes, you'd be right. Ft is 90 newtons to the right. Ff is 90 newtons to the left. They'd both be 90. 90, 90, 100, 100. It would be in equilibrium, it would be at rest, it would be not moving. What would happen if Ft were 50 newtons? newtons. Would FF still be 90? That doesn't make sense. If I pull a block with 50 newtons of force, and there's 90 newtons of force to the left, I'm pulling right, but because of friction it goes left? No, that's not how friction works. It's an inequality. So if Ft is 50 newtons, F would be 50 newtons. Yeah, that makes sense. What if what if Ft were over 90? Let's say it's 110. Well, we found the maximum value is 90, so you'll have the full 90 newtons of friction. The net force will therefore be 20 newtons to the right. Hopefully that makes sense. Seems fine to me. If you know that, you can find the acceleration. (20 newtons over 10 kilograms, 2 meters per second squared, right? Well, you're right for like a millisecond. Let's see. Let me see what I mean. I'm going to change these values. Let's say it's not 100. It's just barely able to move. Let's say I pull with more and more force until the cube just finally starts to move a tiny little bit. So I push with like 90.0000001 newton. Basically 90 if you round to normal sig figs, but a tiny, tiny, tiny bit more. Would the cube accelerate? If so, find the acceleration. It's not a math problem, it's a conceptual problem. Would the cube accelerate? How would you find the acceleration? Okay, here's the trick. I know I was hinting at it last question, and I know you're all dying to know because friction is so much fun. F-U-N, fun, yes. This cube will start moving because the forward force is greater than the backward force. What's the net force? It's not 0. It's not 0.000001. When it's sliding, you switch mu from static to kinetic. So the 90 becomes 80. So 90 newtons to the right plus 80 newtons to the left. F net is 10 newtons to the right. A is F net over m, 1 meter per second squared to the right. So this is a nice idea. If you push something and it just barely starts moving, it barely switches from static to kinetic, that same force will give you a lot of acceleration. Well, not a lot, but a decent amount, because once you overcome the static friction, like I pull on the cube with more and more force. I pull with 50 newtons, I'll pull harder, 60, 70, 80, 90. Once I hit 90, the net force immediately jumps from 0 with the friction and tension canceling all the way up to 10 instantly as soon as it starts moving. That's because we switched from static to kinetic friction. Wow, fascinating. Yeah, that's good. So, in that case, the cube will start sliding. Great, cool, awesome. One tricky-ish, not tricky, but one last thing. So let's say the cube is sliding. it's sliding to the right. What if I want to stop my cube? Let's say it's going too fast. Its velocity is like, I don't know, 100 meters per second. It's a super fast cube. But yeah. So I gotta stop my cube. Well, I'll try to stop my cube. I'm gonna apply a small force. I'm a very small person, so I'm applying a very small force. I put 0.01 newtons of force to the left. Actually, it doesn't even have 0.01. 1 newton. Super small force. If you guys remember, 1 newton is the weight of a very small apple. So I'm pushing the block to the left as it moves to the right super fast. There's a very large velocity to the right. I'm applying a very small force to the left, which is not friction. This is not friction. Will there be friction? Yes. What kind? Static or kinetic? Kinetic, because it is sliding. In what direction? In this case, it doesn't matter that my force is already to the left. The block is sliding to the right, so friction will also be to the left. .8 times 100 newtons, 80 newtons. So there's a very subtle distinction between these two forces besides just their magnitude. Static friction forces oppose other forces. If I push a block to the left, friction is to the right. If I push a block south, friction is north. Kinetic friction, it could oppose other forces, but the rule is it opposes the motion. It's trying to slow down the object. If something is sliding to the left, kinetic friction is to the right. If something is sliding south, kinetic friction is north. So you gotta draw a picture and just identify the direction of friction in problems. Sometimes you won't know the direction because you won't know which way the other force is or the velocity is. So just pick one, draw something. Oh, I think friction will be to the left. If you get a negative answer, that means you were wrong, but then you know to the right. Pretty straightforward. We'll see a lot of practice. I got some spicy problems being cooked up for a lesson 2 days from now. I'll see you guys then.